Welcome to A Brief History of Mathematics, with me, Professor Marcus de Sotoy. This series, first broadcast on BBC Radio 4, is packed with human interest, as well as a solid dose of mathematics. And this is the first of 10 podcasts that you can collect and keep and listen to whenever you wish. The story begins in 17th century Europe, when two men, Isaac Newton and Gottfried Leibniz, were working on an idea that's been described as one of the greatest achievements of mankind. And boy, did they squabble over it. In this brief history, I want to reveal the personalities behind the calculations and show how mathematics drives science forward. 4 centuries ago, Galileo Galilei declared,
"The universe cannot be read until we have learnt the language and become familiar with the characters in which it is written. It is written in mathematical language, and the letters are triangles, circles, and other geometrical figures, without which means it is humanly impossible to comprehend a single word. Without these, one is wandering about in a dark labyrinth."
Mathematics is the light that leads scientists out of the dark labyrinth of misunderstanding. Sure, telescopes and microscopes, observations and experiments have a role to play, but I believe mathematics is the driving force behind modern science. We celebrate the scientific genius of Albert Einstein, but what about the pioneering mathematicians on whose shoulders he undoubtedly stood? Particle physicists today are deeply indebted to a mathematician who was killed in a duel just after the French Revolution. And the mathematics of a Napoleonic soldier is the reason that you can hear me now. I should probably declare an interest at this point. I'm a mathematician, and in my view, mathematics is the language of the universe. Mathematics is the queen of science.
A Brief History of Mathematics with Marcus de Sotoy.
In Europe, in the late 17th century, where this brief history of mathematics begins, two exceptional mathematicians, one pure, Gottfried Leibniz, and the other more applied, Isaac Newton, were working on the same problem at the same time. Sir Isaac Newton, that great hero of British science, was described in an early school report as being
inattentive and idle.
Still, he went on to study at Cambridge, and in his early 20s started work on a new mathematics, the mathematics of moving things, or calculus. He described this new mathematics to friends, but didn't publish any account of how he did it, a decision that was to have ugly consequences. For at the same time as Newton was busy with his calculus, the young German scholar Gottfried Leibniz came up with a different version of the same thing. Now, whatever you thought of calculus at school, I'm here to try and make it clear. Bottom line, the calculus is a way of describing things that change. Take the famous apple that legend has it fell from the tree onto the young Newton's head and inspired his theory of gravity. At any particular point in time, how fast is the apple falling? The speed of the apple I just dropped is constantly increasing as gravity pulls it to the ground. So, how can you calculate what the speed is at any given instant of time? For example, after 1 second, how fast is the apple falling? What about after 2 seconds? Speed is the distance travelled divided by the time elapsed. So I could record the distance the apple drops in the next second, and that will give me an average speed over that period. But I want the precise speed at a precise moment, like now. Well, I could record the distance travelled over a shorter period of time, say half a second or a quarter of a second. The smaller the interval of time, the more accurate my calculation of its speed. But ultimately, to work out the precise speed at a precise moment of time, I need to take an interval of time that is infinitesimally small. But then I'm faced with calculating 0 divided by 0. The calculus makes sense of this seemingly impossible calculation. It tells you what the speed of something is tending towards as you make the time interval smaller and smaller. Calculus is the mathematics of things on the move. In mid-17th century Europe, this new mathematics of moving things was something that both Newton in England and Leibniz in Germany understood. In July 1676, Leibniz, who was travelling round Europe, received a letter from Newton. Newton had sent the letter to Henry Oldenburg, the first secretary of the Royal Society, who'd sent it on to Leibniz. In it, Newton described his version of the calculus. But he didn't share any of the crucial details about how it worked. Instead, he converted them into a curious code.
The foundations of these operations is evident enough, in fact. But because I cannot proceed with the explanation of it now, I have preferred to conceal it thus. 6ACCDAE 13EFF 7I319N 404 QRR 4S8T 12VX.
Newton wanted to stake his claim on the calculus without giving away any of the details. But Leibniz didn't need the details. He understood. He dashed off an immediate and enthusiastic response, expressing admiration for what Newton had told him and presenting some discoveries of his own. Newton's letter, however, had taken 6 months to reach Leibniz. Henry Oldenburg had not been sure where to post it, given Leibniz's peripatetic existence, and when, 6 months on, Newton got a response from Leibniz, he didn't reply. It could have been the beginning of a fruitful exchange of ideas, but it wasn't, and the correspondence ended. Leibniz, meanwhile, set about recording his discovery of the calculus, working on it off and on for almost a decade. When he published it in 1684, the Bernoulli dynasty, a powerful family of Swiss mathematicians, took his ideas and broadcast them widely through the mathematical world. Leibniz began to receive credit for this powerful new mathematics. Newton didn't like it. Newton, by this time, was well established as a great scientist. Aged just 27, he'd been awarded the highly prestigious Lucasian Chair for Mathematics in Cambridge. He'd published countless hugely important scientific papers, including his laws of motion and the famous universal theory of gravitation. He went on to become an MP and was appointed Master of the Royal Mint. By the beginning of the 18th century, Newton was in a position of power.
I do not love to be dunned and teased by foreigners about mathematical things.
By which I think he meant, I do not like people giving Leibniz credit for the calculus, not me. 20 years after their aborted correspondence, rather than crediting Leibniz with having insights of his own into the calculus, Newton decided that Leibniz had stolen his ideas and spent 6 months working on them before replying to him. In 1704, Newton finally published his account of the calculus as an appendix to his book on optics. In it, he added a comment that implied that Leibniz had copied his work.
Some years ago, I lent out a manuscript containing theorems about the calculus, and having since met with some things copied out of it, I have on this occasion made it public.
So began a campaign by Newton to claim that, while Leibniz may have published before him, it was he, Newton, who invented the calculus. For Newton, there was no question of sharing the credit. Leibniz, on the other hand, believed,
It is not a quarrel between Mr. Newton and myself, but between Germany and England.
In 1714, after years of acrimony and accusation, the Royal Society in London was asked to adjudicate between the rival claims. Was Newton the first to discover the calculus with his method of fluxions? Or was the credit due to Leibniz with his invention of the differential method?
The differential method is one and the same with the method of fluxions, excepting the name and mode of notation, and therefore we take the proper question to be not who invented this or that method, but who was the first inventor of the method. For which reason we reckon Mr. Newton the first inventor.
Leibniz, who published 2 decades before Newton, was nevertheless accused of plagiarism, and Newton was honoured with the discovery of the calculus. But the Royal Society's report was probably not the most impartial. The report was written by Sir Isaac Newton. When Newton died in 1727, he was given a state funeral and buried in Westminster Abbey with honours normally reserved for a general. Leibniz's memorial, by contrast, is a simple plaque erected in a small church in Hanover. But it is Leibniz's account of the calculus which eventually triumphs, not Newton's. Leibniz was lucky enough to have the backing of the influential Bernoulli family. The Bernoulli family became Leibniz's disciples, taking his mathematical messages, clarifying them, realizing their deep implications, and spreading the word across Europe. In particular, the Bernoullis realized just how powerful Leibniz's calculus was for finding the best solution to all manner of problems. This is the real power of the calculus, its ability to home in on the most efficient solution. It's this that makes it one of the most important tools in modern science. The natural world is in a constant state of flux. So many things are on the move, and if you want to understand and predict such things, calculus is invaluable. Designers use it to optimize construction. Engineers exploit it to minimize energy use or maximize the speed of planes, trains, and automobiles. Space travel depends on it.
The basic rocket equation, which tells how rockets work, uses the calculus.
Astronaut Jeff Hoffman. But does he ever think about Newton and his calculus when he's out there in space?
I have to admit that there are so many other things to do that I really wasn't thinking that much about the history of science as we were approaching the Hubble Space Telescope, getting to reach out with the mechanical arm and grab it. There's lots of other things on your mind. But it's nice to know that Newton is safely ensconced in the computer and that his mathematics is guiding us on our path to a successful mission. You know, space travel without Newton and his calculus would just be inconceivable.
Calculus is one of the linchpins of our modern technological world. The calculus underpins our understanding of so many things: mechanics, electricity, magnetism, the solar system. I could go on and on. It's a stunning mathematical insight that's had a profound, wide-reaching and long-lasting impact on science. And it's not just in the world of science that it's found a use. Every day, across the industrial and financial world, investors use the calculus that Newton and Leibniz started to maximize profits. Matthew Killier is a quantitative analyst for a hedge fund.
The kind of scientific hedge funds at the time we're trying to use mathematical modelling to help predict the world's financial markets, to make bets in the world's financial markets. It's quite staggering to step back and realise that every day you're entrusting $13 billion to a computer which is using mathematical models and code which are crucially underpinned by the ideas and equations from calculus, an idea that was formalised over 300 years ago.
To say calculus is one of the greatest achievements of mankind is, I think, entirely justified. And it's the calculus of Leibniz, not Newton, that proved to be the most powerful. As a pure mathematician myself, I have to say it pleases me that it was the pure mathematics of the humble Leibniz, rather than the more applied approach of the more scientifically minded Newton, that eventually triumphs. But with the benefit of hindsight, it's clear that both men's analysis left a lot to be desired. Tomorrow we'll meet the man who stood on Newton and Leibniz's shoulders and realised the true power of the calculus. Thanks for listening to this podcast from BBC Radio 4 with me, Marcus de Sotoy. And if you enjoyed this episode, don't forget you can collect the whole set, all 10 episodes of A Brief History of Mathematics, as well as the terms and conditions, can be found at bbc.co.uk/podcasts. Hello, I'm Professor Marcus de Sotoy, and this is a podcast of Episode 2 of A Brief History of Mathematics, first broadcast on BBC Radio 4. I think of Leonhard Euler as the mathematician's mathematician. No history of mathematics is complete without him. In the year Isaac Newton died, Euler, then aged just 19, was awarded the most prestigious mathematical prize of the day, the first of many, many achievements and accolades he would receive during his lifetime. The annual mathematical challenge issued by the Paris Academy of Science in 1727 was this: What is the best way to arrange masts on a ship? At first sight, it's a very practical problem, but the young Swiss mathematician Leonhard Euler attacked it as a purely mathematical puzzle. Despite having never set foot on a ship, he felt perfectly well qualified to calculate the optimal arrangement of masts. For him, it was a problem that could be solved by mathematics alone.
I did not find it necessary to confirm this theory of mine by experiment, because it is derived from the surest and most secure principles of mathematics, so that no doubt whatsoever can be raised on whether or not it be true, and takes place in practice.
Leonhard Euler had absolute faith in mathematics. He's one of the most prolific mathematicians of all time. There are just so many mathematical ideas named after him. 50 years after his death, his work was still being published. He overhauled almost every area of mathematics. And, almost as an aside, he solved a popular 18th century conundrum about the 7 bridges of Königsberg.
For Euler, solving the problem was an entertainment, was something to do. And of course he could have had no idea how we would build on his work, build on his insights, and use it to create and run a network that has changed the world completely.
The Internet. For Euler, the problem was really just a piece of light relief. But the mathematics he produced when solving it has since transformed the Internet. It's now used to make search engines much more efficient.
A brief history of mathematics with Marcus de Sotoy.
From an early age, Leonhard Euler
calculated without any apparent effort, just as men breathe, as eagles sustain themselves in the air.
He proved theorems for fun, but his father, who was a clergyman, wanted him to train for the ministry.
I had to register in the Faculty of Theology, and I was to apply myself to the Greek and Hebrew languages, but not much progress was made, for I turned most of my time to mathematical studies, and by my happy fortune the Saturday visits to Johann Bernoulli continued.
Johann Bernoulli was an outstanding mathematician based in Euler's hometown of Basel, where in the 18th century the Bernoulli family had a sort of mathematical monopoly. They produced 8 outstanding mathematicians in just 4 generations. Johann tutored Euler and persuaded his father to let him study mathematics instead of religion. And it was Johann's son Daniel, a great friend of Euler's, who found him his first job at the academy in St. Petersburg, where Daniel was based. It was in the medical department, which wasn't ideal, but before he left for Russia, Euler read all he could about medicine. Such was his mindset, he managed to turn even the physiology of the ear into a mathematical problem. But when he arrived, he moved quietly from the medical section to the mathematics department, and nobody seemed to mind. And it was while he was here in St. Petersburg that Euler learnt about the well-known Königsberg bridges problem. The Prussian city of Königsberg was split into 4 distinct regions of land by the several branches of the river Pregel. 7 bridges connect these 4 different areas, and in Euler's day it had become a Sunday afternoon pastime among residents of the city to see whether they could find a way to cross all the bridges once, and once only, and get back to where they'd started. Euler wrote to the court astronomer in Vienna, telling him what he thought of the problem.
This question is so banal, but seemed to me worthy of attention in that neither geometry nor algebra nor even the art of counting was sufficient to solve it. In view of this, it occurred to me to wonder whether it belonged to the geometry of position, which Leibniz had once so much longed for. And so, after some deliberation, I obtained a simple, yet completely established rule, with whose help one can immediately decide for all examples of this kind whether such a round trip is possible.
Instead of endlessly walking around the town, testing out different routes, Euler created a new geometry of position, in which old-fashioned measurements like lengths and angles, all measurements in fact, were irrelevant. What matters is how things are connected. It's the same principle that's used in the map of the London Underground. The London Underground map is not a physically accurate map. I'm at Temple Tube Station, and on the map, it's quite a distance from Embankment. Actually, it looks much closer to Blackfriars. But in reality, Blackfriars and Embankment are about the same distance away from Temple Tube Station. If anything, Embankment is probably slightly closer. But this is the beauty of the tube map. Measurements are unimportant. What matters is how the stations are connected together. And this is exactly the kind of logic that Euler applied to the problem of the bridges of Königsberg. Euler decided to think about the different regions of land in Königsberg that were separated by the river as points or stations, and the bridges linking them as lines connecting them. And what Euler figured out is this: for a round trip, without retracing your steps to be possible, every point or station, except the beginning and the end, must have an even number of lines coming in and out. Not surprisingly, if you apply this to the circle line, you find that a round trip without retracing your steps is quite possible, as every station has just two lines attached, one going in and the other coming out. Applied to such a simple case, it's hardly rocket science, you might think. But the clever thing about Euler's rule is that it works in any situation. When Euler analysed his London Underground style map of Königsberg in this way, he found that every point or bit of land had an odd number of lines or bridges emerging from it. So, without having to endlessly walk around the town, he figured out mathematically that it just isn't possible to walk around the city crossing each of the bridges once and once only. Euler's rule is easy enough to apply. The difficult bit was to frame the Königsberg bridge problem in this way in the first place, and to prove that the number of lines going in and out of any point really is all you need to know to work out whether or not such a trip is possible. And you don't need to be a mathematician to find an insight like this useful. Euler's mathematical solution to the Königsberg conundrum now drives one of the most important networks of the 21st century, the Internet, a network that links millions of computers all the way around the world and moves digital data between them with incredible speed. Technology expert Bill Thompson.
So if I've got my computer at home and I tap away a website or something like that, I need to make a connection from my computer to the computer that's hosting that website. And that could be anywhere. I don't really care where it is. All I want is for the information from that website to get back to me as quickly as possible. And I do that because embedded in my computer and all the computers that make the internet happen are rules based on Euler's work back in the 18th century when he was looking at the bridges of Königsberg and trying to figure out how you can walk around the town.
It was hardly a pressing problem at the time, more of a curiosity. But Euler's solution to this problem lives on and has revolutionized the Internet. I always think of Euler as a sort of mathematical omnivore, a man who would turn anything he could into a mathematical puzzle. As scientific advisor to the Russian government, he prepared maps, advised the Russian Navy, tested designs for fire engines, and wrote textbooks for Russian schools. Although apparently he drew the line when he was asked to cast a horoscope for the young Tsar. But broadly speaking, he was free to do what he pleased. He didn't even have to teach. In the mid-18th century, many European leaders were anxious to attract mathematical talent to boost their prestige. Euler, who not so long ago had struggled to find a job, was now in demand. Frederick the Great wanted his Berlin Academy, founded by the great Leibniz, to compete with Paris and St. Petersburg. It had been a centre of excellence, but was slowly dying due to a lack of great minds. And such was the intellectual zeitgeist of the time, Frederick felt obliged to encourage mathematics, even though he himself was not very good at it. In 1740, he invited Euler to join the Berlin Academy. Euler was delighted.
I can do just what I wish in my research. The king calls me his professor. I think I am the happiest man in the world.
But the honeymoon was short-lived. King Frederick wanted fountains at Sanssouci to rival the French system at Versailles.
I wanted to have a water jet in my garden. Euler calculated the force of the wheels necessary to raise the water to a reservoir, from where it should fall back through channels, finally spurting out in Sanssouci.
For Euler, designing the fountains was a wonderful mathematical puzzle. How does water behave when it's pumped and forced through pipes? To make the puzzle a little simpler, he decided to ignore any friction between the pipes and the water. But there was friction.
My mill was carried out mathematically, and could not raise a mouthful of water closer than 50 paces to the reservoir. Vanity of vanities, vanity of mathematics.
King Frederick teased Euler mercilessly. But as a fellow pure mathematician, I think it's unfair to judge Euler so harshly. Frederick wanted a fountain that he could be proud of. Euler wanted something slightly different. He wanted to understand how fountains work. And, as we've since discovered, the mathematical answer to this is an absolutely fiendish equation. It's an equation that remains unsolved to this day, with $1 million currently on offer for anyone who can crack it. Age 59, Euler returned to St. Petersburg, encouraged by Catherine the Great, where he lived in style with more than a dozen household assistants and meals prepared by one of the court's very own cooks. His sight had been poor for quite a while. When he lost his sight altogether, he simply remarked,
"Now I will have less distraction."
By this time, his reputation as a phenomenal mathematician was well established. Euler had produced a dazzling array of mathematical papers on the theory of numbers, mechanics, and calculus, where he finished what Newton and Leibniz had started. Back in Russia, he wrote yet more papers, approximately one a month, describing the power of the calculus. Euler was a great fan of Newton's, but his drive for rigour revealed Newton's maths to be a little shaky.
Newton was, without doubt, one of the greatest geniuses that ever existed. His profound knowledge and his acute penetration into the most hidden mysteries of nature will be a just object of admiration to the present and to every future age. But the errors of this great man should serve to admonish us of the weakness of the human understanding, which, after having soared to the greatest possible heights, is in danger of plunging into manifest contradiction.
Euler ironed out the manifest contradiction in Newton's calculus. He rebuilt calculus on new, more solid mathematical foundations. To this day, it's a mathematical triumph. Leonhard Euler, the mathematician's mathematician. In the words of the great French mathematician Pierre-Simon Laplace,
"Read Euler. Read Euler. He is master in everything."
If, as you may have heard me argue yesterday, Isaac Newton launched modern science by making it more mathematical, Leonhard Euler launched modern mathematics by, well, making it more mathematical. And it would be upon the mathematical shoulders of Euler, not Newton, that the mathematicians of the next 2 centuries would stand. Thanks for listening to this podcast from BBC Radio 4 with me, Marcus de Sotoy. And if you enjoyed this episode, don't forget you can collect the whole set, all 10 episodes of A Brief History of Mathematics, as well as the terms and conditions, can be found at bbc.co.uk/podcasts. I'm Professor Marcus de Sotoy, and in this podcast of the 3rd episode of A Brief History of Mathematics, first broadcast on BBC Radio 4, musician Brian Eno tells us why he loves the mathematics of Joseph Fourier, an 18th century French mathematician, Napoleonic soldier, and servant of the French Revolution. In May 1798, the mathematician Joseph Fourier received a mysterious summons from the Ministry of the Interior in post-revolutionary France.
"Citizen, the Executive Directory, having a particular need of your talents and of your zeal, has just disposed of you for the sake of public service. You should prepare yourself and be ready to depart at the first order."
2 months later, Fourier set sail for Egypt, recruited by Napoleon along with 30,000 soldiers and more than 100 academics, Napoleon's intellectual army. Now, I'm a mathematician. I like to explore the world of mathematics for its own sake, without worrying unduly whether it will be useful. But this is the story of a young Republican who believed mathematics should never forget its role as a servant of the French Revolution. A man for whom the real value of mathematics was its usefulness to society. And useful it proved to be. Fourier's groundbreaking theory of heat led to new ways of understanding not only heat, but light and sound, with some amazing spin-off benefits. Music producer Brian Eno.
Fourier's breakthrough was to realize that fundamentally there was only one kind of waveform, so it was like an atomic theory of music, if you like.
This, for Fourier, and for me, is the power of mathematics. Its ability to generalize results beyond their original context, and to find applications far beyond anything anyone might have expected.
A Brief History of Mathematics with Marcus de Sautoy.
Joseph Fourier, the orphan son of a tailor, discovered the magical world of mathematics as a young teenager. At his military boarding school, he collected candle ends and studied into the night while the other boys snored. There was no one to supervise him, but it seems he didn't need anyone to tell him that he was good. He knew. He wanted to join the military, but his application was denied.
Fourier, not being noble, cannot enter the artillery, even if he is second to Newton.
But the French Revolution of 1789, which he supported, changed everything. The new republic in France founded centres of learning to cultivate the new thinkers of this revolutionary age. Students were chosen on the grounds of intelligence and knowledge alone. No one, it was thought, should be denied a place for lack of funds. And of all the disciplines, mathematics and science were the most highly praised.
Citizen, the revolution not only improves our morals and paves the way for our happiness and that of future generations, it even unlooses the shackles that hold back scientific progress.
And Fourier's talents, not only as a mathematician but also as a teacher, didn't go unnoticed. He was appointed head of mathematical education in the new École Polytechnique. It was a real innovation to have mathematics taught by those who were actually creating it. For the first time, mathematical lectures became real performances. Professors had to deliver their lectures standing up, with no notes and no desk to hide behind. Dialogue and debate were expected between the lecturer and the students. Fourier in particular thrived.
He has a loud voice, is active, ingenious, and very learned.
A great performer, he loved giving lectures, and he'd intersperse his mathematical exposition with interesting historical references, and he always tempered the abstract side of the subject with more practical applications. Fourier's oratory skills have been put to use advocating the political revolution. Now they were employed in propagating a mathematical revolution. Before long, he was spotted by Napoleon himself and received that mysterious summons to set sail for Egypt. After the Battle of the Pyramids, Napoleon returned to France, and Fourier was left stranded in Cairo, not being sufficiently well connected to avoid the charge of desertion. In 1799, he helped to discover the Rosetta Stone, and it was here in the middle of the Egyptian desert that Fourier fell in love with heat. And not just the mathematics of it. He believed it had fantastic medicinal powers. When he returned to France, his friends would find him sitting in his wildly overheated room in Grenoble, wrapped up like an Egyptian mummy, sweating, and we can only assume contemplating the mathematics that would help him to explain exactly how heat behaves. Even before he'd answered the question he'd set himself, how does heat vary over time, Fourier knew just how important the answer would be, not just for the understanding of heat, but for the whole of physics.
Heat, like gravity, penetrates every substance of the universe. Its rays occupy all parts of space. The object of our work is to set forth the mathematical laws which this element obeys. The theory of heat will hereafter form one of the most important branches of general physics.
And his prediction was not wrong. Fourier's mathematical understanding of how heat varies has enabled us to understand anything which can be described as a wave. Heat, sound, and light can all be described as waves. And if understanding sensations like these isn't useful, I don't know what is. Here's someone who understands sound better than I do, music producer Brian Eno.
The great insight of Fourier was that every wave, however complex it was, could be expressed as the sum of lots of sine waves.
Sine waves are the simplest waves there are. On paper, they look rather like a child's drawing of the Loch Ness Monster, a series of smooth, regular, up and down curves. But what do they sound like?
A sine wave is the purest, simplest waveform and very boring to listen to. Because it has no personality at all. It's a sound with almost no personality. For it to have personality, you have to add other harmonics to it. And of course, what distinguishes instruments from each other largely is the harmonic structure of them. So a violin has a different harmonic structure than a trumpet, and you can class instruments by their harmonic structures, like a lot of woodwind instruments have similar harmonic structures. But that was not at all evident at the time of Fourier. They all just sounded like lots of different things.
Every sound can be described by a waveform. If you've got an equalizer on your radio, the dancing lights jumping up and down right now represent a simple waveform of the sound of me coming from your loudspeaker. The simplest sound wave there is this. The pure sound of a tuning fork. It's called a sine wave, or the Loch Ness wave if you prefer. This, however, is a much more complicated sound. The waveform looks like a kind of mountain range with countless peaks, all of different steepnesses and heights. Fourier believed if he could get to the bottom of all these different waveforms, break them down into their simpler pieces, then he'd be onto something. He was looking for the underlying principles that determine their very different shapes. And his revelation was this: every waveform, no matter how complicated and jaggedy, can be broken down into a basic set of simple, smooth sine waves, those Loch Ness lookalikes, like this one. Or, put another way, if you add up lots of simple sine waves of different frequencies, that is, Loch Ness curves with the bumps more or less squished together, you can reproduce the jaggedy mountain-like profile of the trumpet. This is the grammar of waveforms. It explains how they all relate to one another. And this is what Fourier's groundbreaking theory of heat was all about. Fourier studied heat, but his mathematical analysis applies to sound as well. In fact, it works for anything that can be described as a wave. As Fourier says,
mathematics compares the most diverse phenomena and discovers the secret analogies that unite them.
Fourier's analysis of heat is a brilliant piece of pure mathematics that explains the behaviour of heat, light and sound and plenty else. But when he first published, his mathematics met with some vigorous opposition. Many fellow academics were sceptical. It seemed impossible that smooth sine or Loch Ness waveforms could ever produce such complicated, jagged-edged waves of, say, the trumpet. Leading mathematician Pierre-Simon Laplace wrote,
"The manner by which the author has reached his equations is not exempt from difficulties, and his analysis to integrate them still leaves something to be desired, even on the side of rigour."
And believe me, to accuse a mathematician of lacking rigour is tantamount to telling Brian Eno he's tone deaf. But Fourier remained confident and continued working on his treatise, publishing the final version in 1822. Coincidentally, the same year that the Rosetta Stone was finally decoded. It took several years for Fourier's achievements to be recognised, but when they were, there was no holding back on the praise. Lord Kelvin, the man after whom the modern scientific unit of temperature is named, declared,
Fourier's is not only one of the most beautiful results of modern analysis, but it also furnishes an indispensable instrument in the treatment of nearly every recondite question in modern physics. Fourier is a mathematical poem.
Fourier's early prediction that the theory of heat will hereafter form one of the most important branches of general physics was spot on. It describes not only heat, but light and sound, anything, in fact, that can be described as a wave. It gives us a way of thinking about these very real phenomena. It's also the reason your radio, CD player or iPod works. They simply tell your speaker to vibrate, to create all the simple sine waves or Loch Ness waves that make up a particular sound. Played simultaneously, these simple waves miraculously recreate the sound of me, an orchestra, or Brian Eno in your living room.
And now there's a new generation of processing tools which are based on fast Fourier transforms, which means real-time transforms, where what's happening is that the computer is looking at sound in exactly the way that Fourier suggests, breaking it into individual waveforms. And therefore allowing you access to parts of the sound that really you never could get to before. Particular harmonics, for example, which you could then delete or change or amplify or slow down or whatever you want to do. So the modern translation of Fourier is that we now can get inside sound in the same way as a nuclear scientist can now get inside atoms.
And this power to get inside sound has generated music that has never been heard before.
So I've just recorded a Chinese tea tray and turned it into a musical instrument like this. Okay, now if I apply a fast Fourier transform to it and then start doing things with the individual parts of the sound, this is the kind of result I get. There's a lot of personality in that, isn't there? A lot of movement within it. Just to remind you, that same sound without the fast Fourier transform is...
The amazing power of mathematics. Joseph Fourier believed
the profound study of nature is the most fertile source of mathematical discoveries.
Fourier's study of heat, inspired perhaps by his time in the Egyptian desert, led, as he himself predicted, to one of the most potent mathematical ideas of all time: Fourier analysis, the grammar of waveforms. Fourier wanted his mathematics to be useful. It certainly is. Thanks for listening to this podcast from BBC Radio 4 with me, Marcus de Sotoy. And if you enjoyed this episode, don't forget you can collect the whole set, all 10 episodes of A Brief History of Mathematics, as well as the terms and conditions, can be found at bbc.co.uk/podcasts.